All right, so let's go back a little bit into the tick rate section. I kind of want to read a little slower so that we get a good grasp of timers. I think this chapter is the only time where it's discussed in detail, so it's worth just making sure we understand things. So anyway, uh, tick rate, hertz. So hertz, Hz. The frequency of a system timer, the tick rate, is programmed on system boot based on a static preprocessor defined hertz. So this is a macro variable like we saw yesterday. It's in the source code. It's really dependent on the architecture that your OS is going, or the kernel is going to be compiled onto. So if you're compiling for x86, for example, this define right here will use the x86 value. If you're on ARM, it'll be on the ARM value, and so forth. So again, there's like a bunch of kernel configuration variables that you can use to kind of compile against a specific architecture, and so there's like, just think of it as like an if else to include the right file. So the value of hertz differs for each supported architecture. On some supported architectures, it even differs between machine types. The kernel defines a value in ASM param.h. The tick rate has a frequency of hertz and a period of 1 over hertz seconds. Okay, so for example, by default, the x86 architecture defines hertz to be 100, so 100 hertz, 100 times per second. Therefore, the timer interrupt on the i386, which is a CPU, has a frequency of 100 hertz and occurs 100 times per second. Okay, so hertz is the frequency. How many times per second? So 100th of a second, which is every 10 milliseconds. So the timer ticks every 10 milliseconds. So every 10 milliseconds, timer just goes off with an interrupt. Okay, so the timer interrupt ticks every 10 milliseconds for i386, meaning any 32-bit x86 CPU. Because the reason why they call it i386 is because the 386 was the first 32-bit x86 CPU from Intel. So other common values for hertz are 250 and 1000. So 1000 times per second. So basically 1 over 250 seconds, the interrupt will fire, or 1 out of 1,000 times per second, the interrupt will fire. So for computers like this, where the tick rate is 1,000, or like the frequency is 1,000, you're thinking like 1 millisecond every single time the interrupt is gonna fire. So that's very, very often. Corresponding to period of 4 millisecond and 1 millisecond respectively. Yeah, so this one's 4 milliseconds and this one's 1 millisecond. Table 11.1 is a complete listing of the supported architecture and their defined tick rates. So here's a table here. They're mostly all just 100 except for Alpha, which I don't think there's any other new CPUs coming out for Alpha anymore. Yeah, so I think x86 also encompasses x86 64 too, so AMD 64 architecture. So any of our modern new CPUs in this case. When writing kernel code, never assume that hertz has any given value. This is not a common mistake these days because so many architectures have varying tick rates. In the past, however, Alpha was the only architecture with a tick rate not equal to 100 hertz. And it was common to see code incorrectly hard code the value 100 when the HZ variable, this define value, should have been used. So don't hard code tick rates in kernel code. Use the HZ define. Okay. Example of using HZ in kernel code are shown later. The frequency of the timer interrupt is important. As you already saw, the timer interrupt performs a lot of work. Indeed, the kernel's entire notion of time derives from the periodicity of the system timer. Sorry, there's this edge popping out at me on my streaming computer. I can't see crap. Okay, picking the right value, like a successful relationship, is all about compromise. So the ideal Hertz value. Starting with the initial version of Linux, the i386 architecture has had a timer interrupt frequency of 100 Hz. So it's always been every 10 milliseconds. So, in fact, like, this is the reason why you shouldn't, I guess, try to schedule things less than 10 milliseconds on i386 because there's no point. The timer interrupt doesn't even fire anyway. So, during the 2.5 development series, however, the frequency was raised to 1000 Hertz, and as such things are controversial. Although the frequency is again 1000 Hertz, it is now a configuration option, allowing users to compile a kernel with a custom Hertz value. So we can actually do like 200, 300, 400, and so on to get more granular. Because so much of a system is dependent on the timer interrupt, changing its frequency has a reasonable impact on the system. Of course, there are pros and cons to larger versus smaller Hertz values. Increasing the tick rate means the timer interrupt runs more frequently. Consequently, the work it performs occurs more often. This has the following benefits. The timer interrupt has a higher resolution. Okay, so increasing the tick rate means you're going to have a higher resolution of time, and consequently all time events have a higher resolution. So if you do adjust it instead of every 10 milliseconds to like 4 milliseconds or 2 milliseconds, you could do things in more granularity. The accuracy of timed events improves. Okay, I wonder what's the typical hardware timer frequency. Let's see. Computer hardware or real-time clock. Is that what RTC frequency? Okay, so the frequency of real-time clock is typically 32 kilohertz. Okay, is this the one that's used for timer? Let's see. Computer CPU timer hardware frequency. Okay. So basically it's what? Clock rate. How many timers does a CPU need? Let's see. Is it the same clock rate as the real CPU frequency? Let's see. The exact frequency of the timer. So, okay, hardware timer. So it looks like it varies. It depends on the hardware. Huh. So this one is 115 kilohertz for this microcontroller. So I guess this is beyond me. This is beyond my knowledge. It's some number of megahertz. Let's just say that it's probably way more than what you can configure anyway. Modern clocks are originally generated by quartz crystal oscillators of about 20 megahertz and so. Okay. So hardware. What is the CPU clock physically? So it looks like there are clock oscillators that are about 20 megahertz and then multiply to get, I guess, the signals for the CPU clock. Okay, sure. But it looks like it's always like some several thousand kilohertz or some several hundred kilohertz to megahertz, which it means that it's just way more precise than whatever you can do here anyway. So maybe somebody can comment on the video or something, they know better. I personally don't know. So anyway, the accuracy of timed events improves, which makes sense because you can be more precise with your timing. Okay. The resolution increases by the same factor as a tick rate increases. So resolution gets higher if your tick rate increases, which makes sense because if you go from 100 to 200, you pretty much halved the interval from 10 to 5 milliseconds. So for example, the granularity of timers with Hertz 100 is 10 milliseconds. In other words, all periodic events occur along the timer interrupts 10 millisecond period and no finer precision is guaranteed. So you can't go better than 10 millisecond periods if your HZ is 100. With HZ 1000, however, resolution is 1 millisecond, which is 10 times finer. So you can schedule things in 1 millisecond precision if your HZ is 1000. Although kernel code can create timers with 1 millisecond resolution, there is no guarantee the precision afforded with Hertz 100 is sufficient to execute the timer on anything better than 10 millisecond intervals. So no guarantees better than 10. Likewise, accuracy improves in the same manner, assuming the kernel starts timers at random times. The average timer is off by half the period of the timer interrupt because timers might expire at any time, but are executed only on occurrences of the timer interrupt. Okay, so this is kind of important to know. So let's read this again carefully. Okay. Likewise, accuracy improves in the same manner. Assuming the kernel starts timers at random times, the average timer is off by half the period of the timer interrupt because timers might expire at any time, but are executed only on occurrences of the timer interrupt. So for example, with HZ100, the average event occurs plus equal 5 millis or plus minus 5 milliseconds off from the desired time. Thus, error is 5 milliseconds on average. Okay, so half. With Hertz 1000, the average error drops to 0.5 milliseconds, a tenfold improvement. So why is that? If we look at it, thinking about it, if let's say this is like a timeline, right? Why is it so thin? Oh yeah, because of this. Okay. Okay. So we look at some time here. Okay, and this is like 0 or like this. No arrows. 0. Let's say this is like 5 and this is like 10 and then this is 15. This is 20 and then this is like 25. Okay, so if the timer kind of always ticks at intervals of 10, and we happen to have scheduled something right here, right there, time is gonna pass, right? But when the timer interrupt ticks to check to see if something has expired, this thing hasn't yet because let's say we scheduled this for 10 milliseconds, right? To occur 10 milliseconds from now. Just pretend. Actually, let's not confuse ourselves. Let's schedule this for 20 milliseconds to occur. So when this timer fires, this timer interrupt fires, nothing is run yet because this event or this timer hasn't expired. So we go here, right? So this is 5 milliseconds has occurred. This one is another 5 milliseconds has occurred, right? It'll just keep running. Okay, 5 milliseconds has occurred. So, but then the timer interrupt, when it checks, right, it fires at 20, it only sees, okay, well, 5, 10, 15, okay? So it keeps going, okay? And at this point, technically, this extra 5 milliseconds is actually where the event should have expired, right? It should have fired, right? But the timer interrupt doesn't fire then, only until it expires at the 10 millisecond again when it's like 30. milliseconds in this case. Okay, so that to me that makes sense, because here is when in the real world this has expired, but the interrupt hasn't occurred yet to kind of handle that in this case. So there is some precision loss if you're gonna schedule something at a moment where it's kind of random. So advantages with a larger hertz. This higher resolution and greater accuracy provides multiple advantages. Kernel timers execute with finer resolution and increased accuracy. So larger hertz gives you more finer resolution and increased accuracy for kernel timers. This provides a large number of improvements, one of which is the following. System calls such as poll and select that optionally employ a timeout value execute with improved precisions. Measurements such as resource usage or the system uptime are recorded with a finer resolution. So fractions of seconds now, or fractions of milliseconds now. Process preemption occurs more accurately. So switching, right, again, switching, context switching, or with the scheduler, if you wanted to switch more often, this would help increasing the resolution. Some of the most readily noticeable performance benefits come from the improved precision of poll and select timeouts. Okay, so we increase the timer frequency, we actually get some performance benefits, mainly because things are more active at certain intervals. The improvement might be quite large. An application that makes heavy use of these system calls might waste a great deal of time waiting for the timer interrupt. So yeah, if let's say your timer interrupt is like every 100 milliseconds now, then these two system calls are dependent on timeouts, right? Or like the interrupt, that timer interrupt firing are gonna fire less, and thus they're not gonna get as much activity. And that actually leads to a little bit of lag. So if you're aggressive with your resolution time, these things can finish or start working more often. So yeah. Okay, let's read that again. The improvement might be quite large. An application that makes heavy use of these system calls might waste a great deal of time waiting for the timer interrupt, when in fact the timeout has actually expired. Okay, so it goes back to this situation again. Okay. Remember, so it's expired, but the timeout, the timer interrupt didn't fire yet, so it hasn't addressed the event that has occurred. So remember, the average error, that is the potentially wasted time, is half the period of the timer interrupt. Another benefit of a higher tick rate is the greater accuracy in process preemption, which results in decreased scheduling latency. Yeah, because there's like that overhead in scheduling if you have higher or lower tick rates, right? Higher tick rates will allow you to schedule more frequently. So recall from chapter 4 that the timer interrupt is responsible for decrementing the running process's time slice count. When the count reaches 0, need reschedule is set and the kernel runs the scheduler as soon as possible. Now assume a given process is running and has 2 milliseconds of its time slice remaining. In 2 milliseconds, the scheduler should preempt the running process and beginning executing a new process. Okay, so let's say a process has 2 milliseconds remaining in its time slice, and so in 2 milliseconds, we do expect that the scheduler should preempt, meaning kick off that process and bring in a new process to run. Okay, but unfortunately this event does not occur until the next timer interrupt, which is definitely not going to be in 2 milliseconds, right? So at worst, the next timer interrupt might be 1 hertz of a second away. Okay, so 1 over 100 would be every 10 extra milliseconds in this case. So with a hertz of 100, a process can get nearly 10 extra milliseconds to run. So even though this process, for example, has 2 milliseconds left in its time slice, if we're using scheduling involving time slices, even though it has 2 milliseconds left, when it expires, the timer interrupt hasn't fired yet. And at the worst case, the timer interrupt can actually fire in the next period, which is 10 milliseconds from now in order to address that scheduling thing, that preemption to occur, meaning that this process, which really had 2 milliseconds to execute, gets actually 10 extra milliseconds, meaning that it had 12 milliseconds to do a lot of work. Okay, I recall there was a talk by Yao Yue from Twitter, a performance talk. She actually noted this too with when it comes to scheduling in containers, right? So like virtualization containers isn't true like isn't like running on true hardware, so it's still kind of like in process context. You kind of think about it, so it's still at the mercy of the host scheduler, and potentially like you can't really think that having a C group limitation is going to restrict that container from being really bad in terms of using all the resources at that moment of its C group, because your scheduler and things that check for these resource usages are dependent on the timer interrupt. And if the timer interrupt isn't firing that frequently, potentially your container, that misbehaving container, can actually run for much longer, sucking up more resources than it's actually allocated for C group usage. So this was like a talk that was done like I think like 5 years ago or something like that, but not sure if it's still relevant today. But that was really interesting to hear because of timers. Okay, anyway. Of course, this all balances out and fairness is preserved because all tasks receive the same imprecision in scheduling. But that is not the issue. The problem stems from the latency created by the delayed preemption. If the to be scheduled task had something time sensitive to do, such as refill an audio buffer, the delay might not be acceptable. And that's the reason why like sound can start crackling, because there's too much lag in terms of refilling that audio buffer in memory for it to be consumed as sound, right? Increasing the tick rate to 1,000 lowers the worst case scheduling overrun to just 1 millisecond and the average case overrun to just 0.5 milliseconds. I'm just like super curious, like what if I recompile my own kernel to have a higher tick rate and see what happens? Will I actually get more performance on my day-to-day? Disadvantages with the larger hertz. Now, there must be some downside to increasing the tick rate, or it would have been 1000 hertz to start with. Yeah, so there must be a catch for all this, right? Indeed, there is one large issue. A higher tick rate implies more frequent timer interrupts, which implies higher overhead because the processor must spend more time executing the timer interrupt handler. Okay, so that means if you're going to have a higher tick rate and you're firing the timer interrupt way more often, of course, then what is this? You're like, we have to remember that this thing's an interrupt, right? So if it's an interrupt, it's going to interrupt a process. So if this thing's constantly firing, your code is being interrupted all the time, and potentially you don't make progress because this interrupt is happening like 1,000 times per second, for example. So the higher the tick rate, the more time the processor spends on executing that timer interrupt. This adds up to not just less processor time available for other work, but also a more frequent thrashing of the processor's cache and increase in power consumption. Yeah, because your CPU is constantly like doing this work every so often milliseconds. So the issue of the overhead's impact is debatable. Okay. A move from hertz 100 to hertz 1,000 clearly brings with it 10 times greater overhead. However, how substantial is the overhead to begin with? The final agreement is that, at least on modern systems, hertz 1,000 does not create unacceptable overhead, and the move to 1,000 hertz timer has not hurt performance too much. Nevertheless, it is possible in 2.6 to compile the kernel with a different value for hertz. Cool. I should probably check if modern kernel is 1,000 or not. We can just check that, right? So if we go to like kernel.org, for example, to the source code, we can browse 6.13. If we look at, is it include, is it ASM? Include ASM generic? Is that what it is? Params? Is there a param? Right? Okay, hertz right there. Okay, so config hertz. So it's configurable here. is taking it from the config value. But let's look at, see if, geez, isn't it, where would I find it at? Arch? Let's do x86. Let's do include. Let's do asm. Let's do param. Oh, I'm sorry, this might be too small. Okay, let's do param for x86. See if it's changed by default. Param. Is there a param? There's no param. Can we search? Let's see. Let's see. Can we search for hertz? Can we even search the source tree? Ah, just messages. Aww. Let's see here. Where would that structure be? Was it asm param.h? Oops, that's buffer. Asm param.h. Oh, arch. Arch. Include. Arch x86 include asm param.h. Okay. Oops, wrong one. Right there. Arch include. Let's see. Arch. Whoa. This is different now. Arch x86. Okay, Arch x86 include. Okay. Asm. I guess it's not here anymore. It's probably truly configurable now. Okay, so it is configurable now. Yeah. Cool. I guess it's been updated to be fully configurable. Alright, anyway. Interesting. Okay. So I guess the default value is something. We can check that out one day. A Tickless OS. You might wonder whether an operating system even needs a fixed timer interrupt. Although that has been the norm for 40 years, with nearly all general-purpose operating systems employing a timer interrupt similar to the system described in this chapter, the Linux kernel supports an option known as a tickless operation. When the kernel is built with the config hertz configuration option set, the system dynamically schedules the timer interrupt in accordance with pending timers. What? When the kernel is built with the config hertz configuration option set, the system dynamically schedules the timer interrupt. So the system is the one that controls the timer interrupt in accordance with pending timers. So dependent on pending timers. Instead of firing the timer interrupt, say every 1 milliseconds, the interrupt is dynamically scheduled and rescheduled as needed. Oh, okay, so it's kind of just based off of the some state of the system that the kernel decides when to fire a timer interrupt. If the next timer is set to go off in 3 milliseconds, the timer interrupt fires in 3 milliseconds. After that, there is no work for 50 milliseconds. The kernel reschedules the interrupt to go off in 50 milliseconds. Okay, so it's just based off of the workload. Okay, so the reduction in overhead is welcome, but the real gain is in power savings, particularly on an idle system. On a standard tick-based system, the kernel needs to service timer interrupts even during idle periods. Okay, so standard tick-based system. So the whole like tick rate thing, if it's like 100 hertz, then even if the system is idle, the timer interrupt is still firing every 10 milliseconds. Okay, but with a tickless system, moments of idleness are not interrupted by unnecessary time interrupts, reducing the system power consumption. So on tickless systems, it's just based off of like the environment of the system, where if the idle period is 200 milliseconds or 200 seconds, over time the gains add up to tangible power savings. That's cool. I wonder if that's how it is today too in certain systems. All right, so jiffies. Jiffies in a jiffy, be there in a jiffy. The global variable jiffies holds the number of ticks that have occurred since the system has booted. So jiffies is a global variable that continuously increments the number of ticks that has happened since the system has booted. So I guess it's global for all CPUs on the system. So on boot, the kernel initializes the variable to 0 and is incremented by 1 during each timer interrupt. So it's incremented by every timer interrupt. So it's the ticks is basically reflective of every single timer interrupt. So if let's say the timer and ideally let's say that timer interrupt fires 10 milliseconds every 10 milliseconds, and 100 milliseconds has passed, then jiffies would be like 10 or something like that. Thus, there are Hertz timer interrupts in a second. There are Hertz timer interrupts in a second, okay? And there are Hertz jiffies in a second. Okay, that makes sense. Okay, so in 1 second, we fire timer interrupts Hertz times. That means in a second, there are Hertz jiffies, right? So if we fire something 100 times, like the timer interrupt happens 100 times in a second, then we should be getting 100 jiffies in a second. So the system uptime is therefore jiffy over Hertz seconds. Okay, so if we had, let's say, 1,000 jiffies and we had 100 Hertz, right? So 1,000 minus, or 1,000 divided by 100 is 10? Yeah, 10 seconds. So the uptime therefore is 10 seconds. What actually happens is slightly more complicated. The kernel initializes jiffies to a special initial value, causing the variable to overflow more often, catching bugs. When the actual value of jiffies is sought, this offset is first subtracted. Okay, so it's not... What? Okay, but the kernel initializes a variable to 0, but then it initializes jiffies to basically a random special value, making the variable overflow and thus wrap around, catching bugs. When the actual value of jiffies is sought, this offset is first subtracted. What is this offset? Is this the offset of... Oh, we initialize to 0, and then if it's... we assume it's overflowed, so then we 0 subtract that offset to get the real jiffies. Okay. The etymology of the jiffy. The origin of the term jiffy is unknown. Phrases such as "in a jiffy" are thought to originate from 18th century England. In lay terms, jiffy refers to an indeterminate but brief period of time. In scientific applications, jiffy represents various intervals of time, most commonly 10 milliseconds. In physics, a jiffy is sometimes used to refer to the time it takes for light to travel some specific distance, usually a foot or a centimeter across a nucleon. Interesting. In computer engineering, a jiffy is often the time between two successive clock cycles. In electrical engineering, a jiffy is the time to complete one AC alternating current cycle. In the United States, this is 1/60th of a second. Oh, okay, that's why. Okay, so in this case, jiffy is basically the time it takes to complete a specific cycle, and that's... okay, that makes sense. Okay. In operating systems, especially Unix, a jiffy is a time between two successive clock ticks. Historically, this has been 10 milliseconds, so 100 hertz. As we have seen in this chapter, however, a jiffy in Linux can have various values. So it's a jiffy in Linux is just dependent on the configuration of the hertz value we put when we compile the kernel. So if we say we compile the hertz to be 250, then a jiffy is every 4 milliseconds in this case. Okay, so the jiffies variable is declared in linux/jiffies.h as extern unsigned long volatile jiffies. Volatile because it's supposed to change quite often. Let's see if that's consistent with our code. So we can do jiffies.h. Nice. Okay, there's a lot of stuff, but I think we're interested in, these are a bunch of constants. Jiffy 64, I'm guessing. Okay. This 64 value is not atomic, okay? This was mentioned in the other chapter. Sure. Okay, so yeah. In the next section, we look at its actual definition. Okay, so the assignment, that overflow, that random special value. So in the next section, we'll see what is it really assigned to. This is just a declaration, but we want to know what's the definition, meaning that what is it assigned to, which is a bit peculiar. For now, let's look at some sample kernel code. The following expression converts from seconds to a unit of jiffies. So seconds times hertz is going to be from seconds to a unit of jiffies. So, okay, based off of how many seconds has occurred, multiply that by hertz, you'll get the number of jiffies. Okay. Likewise, this expression converts from jiffies to seconds. Okay, so we had 1,000 jiffies happening, and every 100 milliseconds, timer interrupt is fired, so 100 hertz. Basically, 10 seconds has passed. Okay, this all makes sense so far. Okay, the former, converting from seconds to ticks, is more common. So basically, this one, I think, yeah, because remember, jiffy represents the number of ticks that has occurred based off of some hertz value over some time. Okay, so for example, code often needs to set a value for some time in the future. For example, this. So this is how we can calculate how much time we need to execute something from now. So to determine how many seconds, we actually use jiffies, right? So given now, I want to execute specific code that happens at certain time. Well, you start out with this jiffies, which is going to be the timestamp, like right now. And then the next tick is going to be next jiffies plus 1, which makes sense. And then later, okay, so that would be jiffies plus 5 times hertz, which means 5 seconds from now. Okay. And then jiffies plus hertz over 10, which is basically hertz over 10 is precedence. So basically 0.1 second from now. Okay. So we want this to occur. Okay, so jiffies is the current one, right? See, just to review. So if you're saying jiffies plus 1, you want something to happen jiffies plus 1, right? Well, what is 1 jiffy? That is basically your interval, right? So if you want something to happen jiffies plus 1 from now, if you had, let's say, a 250 hertz timer interrupt value, then it's going to be 4 milliseconds from now. But you can also do this type of math too, where it's like, okay, 5 seconds times your frequency, right? So that'll be 5 times 250 will be like what, 5 times. Well, ignoring this is assuming 100, right? So 5 times 50 is like 1,000. So it'll be whatever that is. So, yeah, 5 times 1,000. Yeah. So, no, 5 times 250 is 1,000. 250. Okay. All right. Converting from ticks to seconds is typically reserved for communicating with user space, as the kernel itself rarely cares about any sort of absolute time. Note that the jiffies variable is prototyped as unsigned long, and that storing it in anything else is incorrect, because this thing can go really, 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 really large, I think. Yeah. Okay, so the internal representation of jiffies. So this is the next section they're talking about here. So the jiffies variable has always been an unsigned long, and therefore 32 bits in size on 32-bit architectures and 64 bits on 64-bit architectures. With a tick rate of 100, a 32-bit jiffies variable would overflow in about 497 days. And servers can run way longer than that without rebooting. with hertz increased to 1,000, however, that overflow now occurs in just 49.7 days. So if jiffies were stored in a 64-bit variable on all architectures, then for any reasonable hertz values, the jiffies variable would never overflow in anyone's lifetime. So for performance and historical reasons, mainly compatibility with existing kernel code, the kernel developers wanted to keep jiffies in unsigned long. Some smart thinking and a little linker magic saved that day. As you previously saw, jiffies is defined as an unsigned long. Extern unsigned long volatile jiffies. A second variable is also defined in Linux jiffies on H, which is going to be extern u64. Basically, this is like a macro defined for a 64-bit integer, unsigned 64-bit integer, jiffy 64. The LD script used to link so this is the linker. Wonder if I should go over how these things are read. Yeah, I should do that. So man pages things, okay? When we see a 1 here, when we're reading and they're telling you to refer to a man page, right? And you see LD and then 1 here. 1 is usually going to refer to a command, right? And then 2, I guess, will refer to a standard library call. Let me just make sure. Pages numbers. Yeah. So 1 would be a number, 2 would be a system call, 3, right? So we see something like, for example, print. Oops. Whoa. We see something like print F3 in a book. It means this print F is a C std lib function. 3 hints that. If we see something like ls1, right? That means ls is going to be a command in your system. Okay? If we see something like I don't know, what's a system called? Fork. Okay? If you see fork, you'll most likely see it as fork2. So that's how we actually read the man pages stuff. So, if let's say we wanted to learn more about LD, the book said LD1, okay, we can just execute this command here. So if I were to get out of this place and just do man LD space 1, I'll be going directly to the man page that corresponds to man LD1. Okay. So similarly, if I wanted to read about fork, I could do man fork2. So the system call fork, right? So then I'll be able to go directly to the fork that corresponds to the system call as a reference. So you really think about it, you don't really need the internet to program, right? So it's just, and there's examples here too. So yeah, let's see if it's smart enough. If I just do man fork. Yeah, so on certain things where it's like really unique, like fork, for example, the man page will figure that one out. But occasionally you're gonna have like conflicts, right? So duplicates and things like that. So, oops, wrong one again. That's my other video series. Okay, so so yeah, that's how man pages work. I don't think 6 and 7 really are used. So anyway, is it like this? I may have gotten it backwards, but yeah, just know that they do mean something. So actually, let's just try it. Man 3 fork. Oh, that works too. Man help. Let's see. Man option section page. Oh, okay, so section comes first. Okay. So 3, so it'll be man 3 fork. So, or man 2 fork. Man 2 fork? Man 2 fork. I said man 3 fork? Man 3 fork. So that is a C library function. Okay. So what is the system call version of fork? I remember we read it. It was it create? Man man to create. No. System call. Create process Linux. Forgot already. Fork? No, there was something that fork calls in the background. I just forgot already. Uh-oh. Let's go to, okay, so we're in 214. That's not good. The process. So we look for fork. Fork. What does fork? What does fork call? Do fork. Do fork. Let's see if do fork exists. Man to do fork. No. Man to system? No. Huh. No man pages, I guess, for that. Copy process? Whatever. At least we got this. One man LD. Okay. Is there a way I can list? Let's see. List all man pages in section. Oh, okay. So user share man to. Let's do that. So I can do ls that. Oh, I don't have anything, but I have lots here in 3. Oh, that's interesting. So I don't have any system call ones. That's why. Oh, I wonder how I get system call ones. Oh, I have a Wacom one. So let's see, man for Wacom, my drawing pad. Oh wow, I have documentation for my my what do you call this? My pad. That's cool. That is cool. That is cool. Okay. Anyway. Was it, where is it? Where were we at? Sorry, tangent. Tangent. Okay, internal representations, 214. Okay. Okay, so let's go back to where we were at. LD1 script is used to link the main kernel image. Yeah. Then overlays the jiffies variable over the start of the jiffy64 variable. Okay, so the linker is going to take the compiled, I guess this is the compiled kernel image, VM Linux, and it overlays the jiffies variable. Oh, this is the assembly, okay. Overlays the jiffies variable over the start of the jiffy64 variable, okay. So it reassigns it. Thus, the jiffies is the lower 32 bits of the full 64-bit jiffy64 variable. Code can continue to access the jiffies variable exactly the same as before because most code uses jiffies simply to measure elapses in time. Most code cares about only the lower 32 bits, okay? The time management code uses the entire 64 bits, however, and thus prevents overflow of the full 64-bit value. Okay, figure 11.1 shows the layout of jiffies and jiffies 64. So really, in practice, only the lower 32-bit is used, but possible to access the full 64-bit. Okay. Code that accesses jiffies simply reads the lower 32 bits of jiffy64. The function getJiffy64 can be used to read the full 64-bit value. Such a need is rare. Consequently, most code simply continues to read the lower 32 bits directly via the jiffies variable. On 64-bit architectures, jiffy64 and jiffies refer to the same thing. Code can either read jiffies or call getJiffy64 as long as both actions have the same effect. I think that's just because long and 64-bit architectures are already 64 bits in this case. So I think it's already automatically going to be 64-bit in this case, but this book was written when 32-bit was still like a thing, and I think in 32-bit architectures, long is still a 32-bit number. So and just remember, like, data types in C are they have different widths, right? So C standard data types in 32-bit, for example. Let's see. So yeah, right here. So let's just do this. So let's take a look at, I wonder if there's like a reference for, I think there's like a C types thing. Whoa, that is really inappropriate. Let's close that. Okay. I need to get an ad blocker. Okay, so. Oh, okay. So yeah. So see, so something like this. For example, C will have so for like a signed integer, for example, okay, 1 bit is used for sign, and 15 bits will be the number for a 16-bit machine. So integers are 16 bits for a 16-bit machine. Okay, so that's pretty much, I think, how it works. Storage classes in C. No. So let's see though. Data type ranges. Oh, this is helpful. Here we go. So this one is interesting. There we go. So it will be called long in 32-bit, I guess. Huh. So a long here, an unsigned long, is still four bytes. So it's still 32 bits. Interesting. Yeah. Interesting. So if you use a 64-bit compiler, you'll have to use the U64 thing. Or you can do unsigned long, I'm assuming. Unsigned long. Unsigned long int is 32 bits. Unsigned long will be 64 bits because it's 8 bytes here. Okay. But most compilers will have like aliases for this stuff, like U64 or I guess I64 or whatever. Huh. Learning something new every day. Interesting. Okay, that's it. I gotta stop right now, so talk to you all tomorrow or whenever.